Okay, let's talk about some examples of finding the 3D derivatives in vector calculus, namely the divergence and the curl. And I'm particularly interested in cases when one or the other is 0. So in general, what happens is if the curl of f is equal to 0, we already know that f is actually a gradient. And so what you can spot these by a lot of symmetry in the vector field. And on the other hand, a divergence-less vector field, we actually know that that means the vector field is itself a curl. And so either anti-symmetry, or sometimes, which we'll just, I think it's a little easier to spot, or simply dp dx is 0, dq dy is 0, and dr dz is 0. Of course, the divergence is the sum of all these things, so if each of them is 0, certainly the divergence will be 0 as well. So let's consider some examples of this. I think the example of x, y, z divided by the square root of this vector's length, I think this is one of the most fundamental examples you should be aware of, because I think this example occurs in many places. So this is really just the unit radial vector. And so what we should do now is let's compute the divergence and the curl for each case. So first of all, let's just note that there's a lot of symmetry. Right? I could interchange x, y, and z, and nothing would change really. The vector certainly looks quite similar. But the issue, on the other hand, is what does the divergence look like? So we already know from the symmetry argument that curl f, we should expect this to be true. We should expect to have 0 curl, and so the divergence in general will not be 0. So we'll just have to do the divergence. So let's compute the divergence first. The divergence of f, I'm going to write it as the gradient dot f, and I'm going to use that vector form. So one thing you could do is just compute the divergence honestly and just take partial derivatives. But I think that as mathematicians or scientists, we should be as lazy as possible. So to be lazy, what I'm going to do is use the product rule. So this should be the divergence of the first times the second plus the divergence of the second, or rather the gradient of the second times the first. And this is a dot product, and this is also a dot product because, again, we have vectors. And then this will just be ordinary multiplication because that's just a function. So we need to evaluate the gradient of, the divergence of r. So this is just dx dx plus dy dy plus dz dz. So this is just 3. On the other hand, the next term that we need to think about is the gradient of 1 over r. So I'm going to use the chain rule here to do this one. This should be minus 1 over squared times the derivative of r. And for the gradient of r, here's how I'll do this one. Well, it's the gradient of that square root, right? So let's just do the x part. It's the derivative in x of that square root. So surely that should just be x divided by that square root. Therefore, what the true gradient should be, it should just be all of those components. So it should just be r divided by its length. Oh, if I didn't make clear, r is the length of the position vector. Therefore, we know that this is simply r divided by r. So let's combine all these things. Well, the first term is just 3 divided by r. The second term is just r dotted with itself divided by the length. So we should just get 3 over r plus 1 over r, because obviously this thing is just r squared. So this should just give you 4 over r. That's the divergence. So just a couple of chain rules and product rules. The curl, on the other hand, we're going to have this cross product. We expect this to be 0, remember, by that symmetry heuristic. How do we do this curl? I'm going to, again, be lazy, because that's what we should all strive to be. And I'm going to use the product rule. Avoid using explicit determinant things when you can. So it'll be the curl of the first times the second plus the gradient of the second cross the first. Okay, so in fact, we can actually do this first one quite quickly because, again, by the chain rule, this is just minus 1 over r squared times the gradient of little r. We already did this one. This is just r divided by its length. So now if you're crossing r with itself, certainly we get 0. So this term, that was easy. So now we just have to deal with this term. So I actually claim that the curl of the position vector is 0. One way to see that is just, we note that the position vector is the gradient of r squared. But we can also just do this the honest way. So if we do that determinant, where again, lazy person that I am, I'm using this notation, we will just get I times the determinant that looks like this, and this will be similar. I'm just going to show this one as 0. And this is easy, because this is just dz dy minus dy dz. That's clearly 0. So we get this as 0, therefore the curl of f is 0. Okay, so we have an example where the divergence was not 0 and the curl was 0, but what about the reverse? So what about if we now consider this vector field? F equals 0 cosine xz minus cosine xy. So I'm just going to label these spots as corresponding to x, y, and z, because for the divergence, clearly we want those derivatives. So the divergence of f is simply 0 plus d dy of the cosine plus d dz of that other cosine. Clearly, all of these are 0. So this is one way that the divergence 0 vector fields manifest. They're just missing the correct variables. Another way that it can actually manifest is divergence being 0. The divergence of this vector field in 2D, x minus y, this is actually 0 as well, even though the dependence is not like this one. So let's just see why. dx dx plus d dy of minus y, clearly this is just 1 minus 1, which is 0. And you can see this if you draw this pictorially. What happens is everything looks okay on this axis, but everything is reversed on the y-axis because we have a minus sign. And so what's happening is the streamlines are pointing like this. And so you can see that a net inflow is balanced by a net outflow. And so there's no accumulation or there's no dissipation. So this is the local flow rate of this vector field is 0. So now let's compute the curl. So the curl of this vector field, I don't see a simpler way to do it other than just the determinant. So I, j, k, ddx, ddy, ddz, then we'll have 0 cosine, and then we'll have another cosine. So I am going to expand along. No, I take it back. I'm just going to do it without any special maneuvers. So first we have I times ddy ddz cosine xz minus cosine xy. And then we'll have minus j, and then we'll have this determinant, which is ddx 0, ddz minus cosine xy. Finally, we'll have a plus k times ddx dy 0 cosine xz. So let's just do each term. So this is I times, looks like we're going to pick up a plus. So plus, I think this is x sine xy, and then we'll have a minus, which will get converted into a plus after we differentiate cosine. So I'm going to put a plus there, and then plus x sine xz. And let's do the next term. This is minus j, and then we'll pick up another plus sign. So plus y sine xy minus 0. And then finally for that last term, we'll have this from a minus sign. So minus z sine xz. If you haven't been following along, this is just, I'm using chain rule to differentiate each of these sines and cosines. So we end up getting, well, it's something non-zero, right? I don't think it really matters what it is. It's just, the point is it's not 0. Okay, so there wasn't actually, and the reason you can say that heuristically is it's not symmetric. So it's not equal to a gradient, really, by that heuristic. Okay, hope this was helpful. Thanks for watching.